Okie doke, let's do a little sound check. Quick sound check. Sound check. Okie doke, let's do a little sound check. We're almost ready to go, just waiting for Twitter to play catch up, and then we'll be off to the races. Right, so everything's got up now, so we might as well get started. So this week we are learning HTTP clients in Go. I'm getting through this stuff. I'm silently confident we can get through this by the end of the year, but we will see. There's still some with some hefty like SQL. So let's have a look. Learn HTTP clients in Go. Learn how to use HTTP and Golang to interact with APIs in the web, make requests, handle responses, and use JSON API. Start the course. Okay. Right, so let's get started. So communicating on the web. Instagram would be pretty terrible if you had to manually copy your photos to your friend's phone when you want to share them. Modern applications need to be able to communicate information between devices over the internet. Gmail doesn't just store your emails in variables on your computer, it stores them on computers in their data centers. You don't lose your Slack messages if you drop your computer in a lake. Those messages exist on Slack servers. How does web communication work? When two computers communicate with each other, they need to use the same rules. An English speaker can't communicate verbally with a Japanese speaker. Similarly, two computers need to speak the same language to communicate. This language that computers use is called a protocol. So protocol being communication protocol is a system of rules that allows two or more entities of communication system to transmit information via any variation of a physical quantity. The protocol defines the rules, syntax, semantics, and synchronization of communication and possible error recovery methods. Yep. The most popular protocol for web communication is HTTP, which stands for Hypertext Transfer Protocol. Jello. Throughout this course, we'll be building parts of an online issue tracking app called Jello. It's a typical issue tracker with one key difference. This time, it's good actually. Assignment. Take a look at the getIssueData function that I provided in http.go. It retrieves information about issues from Jello servers via HTTP as a slice of bytes. In main.go, do the following. Convert the slice of bytes into a string using the built-in string type conversion. Print the string representation of the bytes to the console. Oh, I've forgotten all of this now. Okay, so issues string string issues, and then t.print line, is it println, and then I guess issues string. Is that right? Is that... Okay, HTTP requests and responses. At the heart of HTTP is a simple request-response system. The requesting computer, also known as the client, asks another computer for some information. That computer, the server, sends back a response with the information that was requested. We'll talk about The specifics of how the requests and responses are formatted later. For now, just think of it as a simple question and answer system. Request, what issues are on Jello? Response, bug fix, improve, or flow. Which comes first? HTTP request. Oh, let's put the potion on actually. Yeah. HTTP powers websites. HTTP or Hypertext Transfer Protocol is a protocol designed to transfer information between computers. There are other protocols for communicating over the internet, but HTTP is the most popular and is particularly great for websites and web applications. Each time you visit a website, your browser is making a HTTP request to that website's server. The server responds with all the text, images, and styling information that your browser needs to render its pretty website. So it's stuck on my tongue. Got it. So client uses computer server, so user types in https://boot.dev into the address bar. User's computer asks for the website's context via HTTP request. The website server responds with HTML, CSS, JavaScript, and images via HTTP response. Website data is requested via which internet communication protocol? UDP, RabbitMQ, PSQL, or HTTP? HTTP, obviously. That's what we're talking about. HTTP URLs. So a URL, or Uniform Resource Locator, is the address of another computer or server on the internet. Part of the URL specifies where to reach the server, and part of it tells the server what information we need. So this is the general interwebs, and this is like the thing that we want to visit. Put simply, a URL represents a piece of information on some computer somewhere. We can get access to it by making a request and reading the response that the server replies with. Assignment. I've updated the getIssueData function to be a bit more flexible. It now takes a URL as a parameter. Try running the code in its current state. You should notice an error because the URL we're using is invalid. Fix the code so that the call to getIssueData function uses the provided issue URL. This time the printed data won't be as ugly. I added pretty by a function that adds some formatting. Oh. Right, we're back again now. Hey-ho. So, for some reason this isn't running. I don't think there's anything wrong with what I changed, but there we go. No props. Okay, so using URLs in HTTP. So the HTTP :/ at the beginning of a website URL specifies that the HTTP protocol will be used for communication. Other communication protocols use URLs as well, hence Uniform Resource Locator. That's why we need to specify when we're making HTTP requests by prefixing the URL with HTTP. HTTP is the only protocol that uses URLs. So requests and responses quiz. Client makes a HTTP request, server sends an HTTP response with a web page. A client is a computer making a HTTP request, whether it's a phone, a laptop, a desktop, etc. The server is a computer responding to an HTTP request. A computer can be a client, a server both, or neither. Client and server are just words that we use to describe what computers are doing within a communication system. Clients send requests and receive responses. Servers receive requests and send responses. So example code. Does the example code act as a client or a server? Client. The computer responding to requests at the URL is a server. In this course, you'll be using Go's standard net/HTTP package and the HTTP.client to make HTTP requests. In fact, we've already been using it. The HTTP GET function uses the default HTTP default client under the hood. So making a request. So it looks like. We'll go in depth on the various things happening here later, but let's cover some basics for now. So HTTP GET uses the HTTP.default client to make a request to the given URL. REST is the HTTP response that comes back from the server. Defer response body.close ensures that the response body is properly closed after reading. Not doing so can cause memory issues. Input output read all reads the response body into a slice of bytes. Slice of bytes called data. Assignment. There is a bug in the get issues function. It's returning the entire HTTP response instead of the data from the body, a slice of bytes. Fix it so that it returns a slice of bytes. Use IO read all to read the body of the response. Return the resulting byte. It's just the same as what's here, really, isn't it? So we get the response. So web clients, click to view the video.
If you've ever played an online game, you're probably already familiar with the idea of servers. Let's break down the difference between a web server and a web client. Let's start with clients. A client is just any device or piece of software that you use to make a request to a server. Typically, this is done over the internet, but it could be done over any. So a client is usually a smartphone, a laptop, or a desktop. It's whatever the end user is using. But the word client gets a little fuzzy because we don't just use it to refer to the actual physical device. We also use it to refer to the software running on that device that's actually doing the request to the server. So, for example, it might be a web browser that's making web requests to a web server. But we might get even more specific and say that it's the JavaScript running within that specific Chrome tab. And then in a completely different example, it might not even be within a browser, but it might be a native mobile app that's making requests as a web client. It might even be a command line tool compiled and written in Go that's making requests over a network. All of those things, we can just broadly say, this is a web client because it's making requests to a server. So what's a server? Well, it's a machine, or really just a computer, that serves or handles these incoming requests from the clients. And while it's not always the case, most production servers live in some data center somewhere. It's not usually in the user's home. It's probably in some data center that needs to be accessed via the internet. So when a client wants to make a request to a server, it looks up the address of that server by its domain name or URL, and then its request is actually routed directly to the machine that is serving that request at that virtual location on the internet, or again, any. So let's take the example of the web server that runs Boot.dev. It's physically located in a data center in Salt Lake City running on Google Cloud Platform's infrastructure. And when you type in Boot.dev into your address bar, your web browser is acting as the client. It's making a request out to the internet. It's looking up the address of the server, given the domain name Boot.dev. It's finding the physical machine, and that machine's software is handling that request. And it will respond with website assets, things like HTML, CSS, JavaScript, a little bit of structured JSON. Now it's like, why would you use a server at all? Why wouldn't you just run all of this code on the user's device? Well, servers are useful because they allow us to centralize stuff and communicate in real time. So video games online wouldn't be possible without a central server that everyone's connected to and can kind of manage the game state in one location. Google Docs wouldn't work on all your devices if there wasn't a central server keeping track of the state of your document. Servers tend to be very data-driven. They usually don't handle things like rendering or visualizations. They manage the data. They manage the data in the backend, and the client typically handles the visualizations, the UI interactions on the front end.
Oh, just realized we didn't complete that thing, so I'm just going to click it. Now back to here, we already watched the video. So as we discussed, a web client is a device that making requests to a web server. A client can be any type of device, but it's often something users physically interact with. For example, a desktop computer, a mobile phone, or a tablet. In a website or web application, we call the user's device the front end. The front end client makes requests to the back end server. The front end of a website is a web client. A mobile phone is often used as a HTTP client. Web servers. So up to this point, most of the data you worked with in your code has simply been generated and stored locally in variables. While you always use variables to store and manipulate data while your program is running, most websites and apps use a web server to store, sort, and serve that data so that it sticks around for longer than a single session and can be accessed by multiple devices. Listening and serving data. So similar to how a server at a restaurant brings your food to the table, a web server serves web resources such as web pages, images, and other data. The server is turned on and listening for inbound requests constantly. So the second it receives a new request, it can send an appropriate response. Turned on and listening for inbound requests, yeah? So the server is the back end, while the front end of a website or the web application is the device the user interacts with. The backend is the server that keeps all the data housed in a central location. A server is just a computer. Server is just the name we give to the computer that is taking on the role of serving data across the network. A good server is turned on and available 24 hours a day, 7 days a week. While your laptop can be used as a server, it makes more sense to use a computer in a data center that's designed to be up and running constantly. Good web servers are listening for requests only when a client is active, only during business hours, always. A server is the blank of an application backend. Any computer can be a server, but the best servers are made for serving data. True. False, only computers in data centers can be servers. False, all computers are equally good at serving data. True. JSON syntax. How many chapters have we got? Okay. JSON, so JavaScript Object Notation, is a standard for representing structured data based on JavaScript object syntax. It is commonly used to transmit data in web apps via HTTP. For example, the HTTP requests we have been making in this course have been returning Jello issues as JSON. JSON supports the following primitive data types: strings, numbers, booleans, null, and the following collection types: arrays, object literal, and object literals. JSON is similar to JavaScript objects and Python dictionaries. Keys are always strings, and the values can be any data type, including other objects. The following is valid JSON data. Assignment: complete the issues list and user object string constant values. Issue list is a JSON array containing two issues object literals. Should have the following issues. Issues list is a JSON array containing two issues. Like somebody should be staring me in the face here, but I don't know what's wrong. It's fine, isn't it? So it just needs to be the array without anything else around it. Like that. Don't think that's valid though. Expected is valid JSON true. Is valid JSON is false. What's wrong with this? This? It's JSON validator. 100%. What's wrong with this? Because of the white space. Oh, my dummy. Okay, yeah, I'm being dumb. Should just realised I need to have quotes around pretty much everything down. It's JSON, not a thingy objects. Well, this is tedious. Just me being a dum-dum. Oh. Say it's submitted, but went a little bit wonky on the output, so I'll just do it again. It's me being a dum-dum. So decoding JSON. So when we receive JSON data in the body of a HTTP response, it comes as a stream of bytes. As we saw before, we can just convert the bytes to a string, but in Go there's a better way. It's typically best to decode the JSON data into a struct. Take this example JSON data, so unspaghettify code, blah blah blah. To decode this JSON into a slice of issue structs, we need to know the JSON fields and their types. The standard encoding/JSON package uses tags to map JSON fields to struct fields. So struct fields must be exported. Capitalized to decode JSON. Okay. After receiving the response, we can decode it into a slice of issues with the address of operator ampersand. Yes, that's using the pointer thing, yep. If no error occurs, we can use the slice of items in our program. Assignment. In previous lessons, we converted response into slices of bytes and then strings. Now decode the response data directly into a slice of issues and return that instead. So import the JSON package from encoding JSON. So keep it alphabetical, I guess. Coding JSON. Create a nil slice of items. So I guess issues colon equals guess it can be var issues. No. Create a slicer / issue. Create a new JSON decoder using JSON decoder. So decoder equals JSON, so new decoder. Response dot body. Decode the response by using the decoder's decode method. So if error equals a decoder dot decode and then issues error is not equal to nil. Okay, let's have a look at the solution. Same difference. Okay, so JSON review. So JSON is a stringified representation of JavaScript object, which makes it perfect for saving to a file or sending in a HTTP request. Remember, an actual JavaScript object is something that exists only within your program's variables. If we want to send an object outside of our program, for example, across the internet in a HTTP request, we need to convert it to JSON first. JSON isn't just for JavaScript. Just because JSON is called JavaScript object notation doesn't mean it's only used by JavaScript code. JSON is a common standard that is recognized and supported by every major programming language. For example, even though Boot.dev's backend is written in Go, we still use JSON as the communication format between the front end and backend. Common use cases: so in HTTP requests and response bodies, as formats for text files. .json files are often used as configuration files in NoSQL databases like MongoDB, Elasticsearch, and Firestore. Pronouncing JSON, so I pronounce it JSON, but I've also heard people pronounce it JSON, like the name, and even JSON, Frenchly. JSON can only be used in JavaScript programs. False. In JSON, different fields in an object are separated by a comma. JSON is a programming language, plugin for JavaScript, format for communicating and storing data, database format for communicating and storing data. Okay, unmarshaled JSON. We can decode JSON bytes or strings into a Go struct using JSON.unmarshal or JSON decoder. The decode method is a JSON decoder. The decode method of JSON.decoder streams data from an input-output reader into a Go struct, while JSON.unmarshal works with the data that's already in byte format. Using a JSON decoder can be more memory efficient because it doesn't load all the data into memory at once. JSON unmarshal is ideal for small JSON data you already have in memory. When dealing with HTTP requests and responses, you'll likely use JSON.decoder since it works directly with an input-output reader. So example. So a REST is a HTTP response. So defer rest.body.close. Then data error input output read all. Hi peeps out there, hope you're enjoying it. I can see a few in the chat. So data error input output read all, response body. If error is not null, then return there was an error happening. Issues and Marshall. Okay, what's the difference? So decode method JSON decoder streams data from the input output reader into a Go struct, while JSON unmarshal works with the data that's already in the byte format. Using a JSON decoder can be more memory efficient because it doesn't load all the data into memory at once. JSON.unmarshal is ideal for small JSON data you already have in memory. When dealing with HTTP requests and responses, you likely use JSON.decoder since it works directly with the input-output reader. Okay. So update the get issue data in http.go. Change the return signature to return a slice of issues and instead of a slice of byte. Issue. Because the function will now return a decoded slice of issues, change the name from getIssues to getIssuesData to getIssues. Decoded slice of issues. Get the data from the response by using the input output read all, creating a slice of bytes in slice byte. Create a nil slice of issues. So that issues issue. So use JSON unmarshal to get the data from the JSON data, return the issues. So JSON.unmarshal data into issues, return issues nil. Not sure I quite understand the difference. But yeah. Okay. Marshal JSON. So there's a way to unmarshal JSON data. Let me see what unmarshal means. So unmarshal. So unmarshal passes the JSON encoded data and stores the result in the value pointed to by v. If v is nil or not a pointer, unmarshal returns invalid unmarshal error. Unmarshal uses the inverse of the encodings that marshal uses, allocating map slices pointers as necessary with the following additional rules. Okay. So if there's a way to unmarshal JSON data, there must be a way to marshal it as well. I'm gonna ask Grok to explain it more simply. Can you explain marshalling and unmarshalling data in Go? Marshalling and unmarshalling in Go. In Go, marshalling and unmarshalling refer to the process of converting Go data structures like structs, map slices, to and from serializable formats such as JSON, XML, YAML, or protocol buffers. The most common use case is with JSON handled with encoding /JSON package. So marshalling. Definition: converting a Go value struct into serialized format, usually JSON. Okay. Unmarshalling. Converting serialized data back to Go data structure. CD. Okay. Converts a Go struct into a slice of bytes representing JSON data. So, for example, this. So a board, and then marshal that, and then assignment. So complete the marshal all function. It accepts a slice of items, which can be of any type. The expectation is that they are structs of various forms. It should return a slice of bytes. It should return a slice of bytes, I didn't stutter, where each resulting slice of bytes represents the JSON representation of an item in the input slice. If an item can be marshaled, the function should immediately return error. Return the marshaled data in the same order as the inputted items. So it should return a slice of bytes. Okay, so let's start with a we're going to say marshaled slices, and it's going to be byte, and then basically for log fatal. And then is it marshaled slices equals append like that, and then return marshaled slices. It should return a slice of bytes where each resulting slice of bytes represents the JSON representation of an item in the input slice. Slices and go. Slice contain other slices allowing you to create multi-dimensional structures such as blah 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 blah. Nil error, and then nil. But it must be an integer. Code nil value for slice. If item copy Marshall, the function should return an error immediately. Return the Marshall data in the same order as the inputs. Index out of range 0. runtime error index out of range 0 with length of 0. So I guess if slices. I'm not going to waste all my time on here. I'm going to move on. Like get Boots to help me if it's just proving to be a little bit of a pain. Yeah. Right, Boots, let's ask for a little bit of help. I'll pay the price. Yeah, I'll use some of the salmon that I've got. Okay, classic. Go slice trap, young apprentice. You've encountered the dreaded index out of range panic. Let's examine what's happening with your code. So marshaled slices is a slice of slices of bytes. This created a slice with 0 length and 0 capacity. It's an empty slice. Then in your loop you do this. Yeah, I know that's what I'm doing, but like how do I get around it? You're trying to assign index 0, but those positions don't exist yet. The slice has 0 length, so there's nothing to assign to. Here's the key question for you. In Go, there are 2 ways you can add elements to a slice when you don't know the final size ahead of time. One involves built-in function that grows the slice automatically, and the other involves pre-allocating with make. Which approach do you think would work better in this situation? The former. Excellent choice. So the append function is perfect here because it automatically grows the slices needed. So instead of that, how would you rewrite that line using the append? Keep in mind that append returns a new slice, so you'll need to capture that as a result. So append, and then it's marshaled slices, index, like that. Am I close? You're very close. You've got the right idea, but about using append, but there's a small syntax issue. Look what you're trying to append. So you're appending to small slice into index, which would be a single byte element, but you want to append to the entire marshaled slice itself. Think about it this way: marshaled slices, slice of slice, blah blah blah. Data is a single slice of bytes. If you want to add data to new elements, what should be the first argument to the append if you want to add a new element to the marshaled slices collection? Also, do you even need index visible anymore where you're using append? No, I don't. Suppose not. Try again. The other way around. Closer. Alright, getting closer, but still, yeah, so it's still an issue with your range loop now. Look at the index. So for when you use range with only one variable, that variable receives the index, not the actual item. So it's going to have to be like that. So item is actually blah, 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 blah. Okay, just getting used to like little Go syntaxes that are tripping me up. Hey Marto, yeah, I'm doing alright tonight. How are you? Hope you guys are having a good laugh at how bad I am at Go at the minute. It's hilarious for me as well, don't worry about it. Yeah, okay, result. So kind of same thing. Oh, the same, just named differently. Okay, so this next action is going to be XML. Okay. So we can't talk about JSON without mentioning XML. XML, or Extensible Markup Language, is a text-based format for representing structured information like JSON, but different and a bit more verbose. XML syntax. So XML is a markup language like HTML, but it's more generalized in that it does not use predefined tags. Just like how in a JSON object keys can be called anything, XML tags can also have any name. So XML representing a movie. The same data in JSON, like that. XML and blank serve similar purposes, JSON. XML is more verbose than JSON. Why use XML? XML and JSON both accomplish similar tasks, so which should you use? XML used to be used for the same things that today JSON is primarily used for. Configuration files, HTTP bodies. Another data transfer can work with either JSON and XML. Personally, I believe that if JSON works, you should favor it over XML. JSON is lighter weight, easy to read, has better support in most program languages. There are cases where XML might still be better or maybe even necessary, but that tends to be the exception rather than the rule. Which do I, the author of this course, prefer, generally speaking? JSON. which can be used to send data from the browser to a web server. Both. Actually, yeah, both. Map string interface. So sometimes you have to deal with JSON data of unknown or varying structure in Go. In those instances, map string interface offers a flexible way to handle it without predefined structs. Think about it as a JSON object. Think about it. A JSON object is a key value pair where the string is key is a string and the value can be any JSON type. So map string interface is a map where the key is a string and the value can be any Go type. Any is an alias for interface, curly brackets. So assignment. A junior developer's deadline is looming. They've been tasked with creating functions to retrieve and log various resources from Jello's API. Rather than making multiple structs and type-safe functions, the junior developer has decided to make 2 flexible functions. Help them complete their task before their boss, Wayne Lagner, just got that. Wayne Lagner asks them to refactor it. Complete the get resources and log resources functions. So get resources. So get resources takes a URL, a string, and returns a slice of maps and an error. It's a slice of maps because the API responds as an array of JSON objects. Decode the response body into a slice of maps and return it. Okay. Now I'm going to look it up because I just don't remember. I can't remember the thing. It's not ingrained yet. Decode. So decoder equals JSON dot new decoder and get a response dot body. Yeah, so then if error decoder dot decode and what we're capturing, resources error is not equal to nil, then return nil error. Otherwise, return resources. Okay. And then so we've done that one. Log resources. So it takes a slice of maps and prints its keys and values to the console. Because maps are unsorted, we will be adding formatted strings to a slice of and its keys are values to the console. Because maps are unsorted, we will be adding formatted strings to a slice of strings, which is then sorted. Iterate over the slice of map for each. Okay, so for resources, each that get its keys and values using range and append it to formatted strings as key, where S, okay, B is the value, okay. Index, so I guess formatted strings equals append, and then let's do that for now. Like formatted strings. See what it does. You think about how to use string interpolation format strings in Go. So fmt sprint f, and then it's index and resource. Boom. Is that right? Yeah, I think that's right now. Okay, let's see the solution. So pretty much the same. So now we're on to DNS. Let's see if we can get to headers by the end of the night. So web addresses. In the real world, we use physical addresses to help us find where a friend lives, where a business is located, or where a party is being thrown. Well, where a party is being thrown. Well, I don't, because I'm not invited to parties, but I digress. In computing, web clients find other computers over the internet using the Internet Protocol IP addresses. Each device connected to the internet has a unique IP address. So domain names and IP addresses. When we browse the internet, we type in a human readable domain name. The domain is converted to an IP address. The IP address tells our computer where the server is located on the internet. Okay, let's look.
If you want to go to a friend's house, the simplest way is typically for them to send you their home address. You pop it into Google Maps and off you go. The internet, or computer networks in general, are similar to a city full of houses. Each house has an absolute location, a latitude, longitude coordinate, and a label that makes it easier to find that location. No one wants to memorize 37.06 or negative 113.40, so instead we use a human-friendly address, like 356 Huckleberry Drive, and sync that address maps to that latitude, longitude coordinate. Computers work the same way. An IP address is the computer-friendly address of a machine on a network, like the internet. For example, 198.35.26.96. When you visit a website, you're really just making a request to a computer, called a server, that's configured to serve web pages. But it's inconvenient to tell your friend, hey, I found this cool site, go to 132.148.74.10. That's where domain names and DNS, the domain name system, come into play. DNS is like Google Maps in our house example. It takes a human-friendly address, like wikipedia.org, and tells your computer the actual IP address it needs to talk to get to that human-friendly address. And that human-friendly address, wikipedia.org, it's called a domain name. Domain names are for humans, so we don't have to memorize the IP addresses of all the servers we want to contact. It's also worth mentioning that 132.148.74.10 is an IPv4 address, Internet Protocol version 4. But IPv6, or Internet Protocol version 6, is also very commonly used now. And those addresses are practically impossible to remember. I mean, look at this.
Crazy. So, assignment. Cloudflare is a tech company that provides a cool HTTP server that we can use to look up the IP addresses of any domain. I provided a get IP address function that makes a request to Cloudflare. The function takes a domain name as input and returns the IP address associated with that domain. The function currently prints a string representation of the entire response we receive from Cloudflare. So the function currently prints a string representation of the entire response we receive from Cloudflare. So run the code to see the structure of the response and what field it contains. Okay. Run the import encoding JSON package and unmarshal the responses you've done before. So encoding JSON. Unmarshal responses you've done before. Hook the data get IP address function to return just the IP addresses found within if it exists. What's he do? Okay. Update the get IP address function to just return the first IP address found within it. Exists if there are no IP addresses. Address return empty string and an error. Then var DNS response. So var DNS response colon equals rate of DNS response body to DNS response. Update the get IP address to return the first IP address found within. If it exists, if there is no IP address, return an empty string and an error. No IP address found. So I guess for responses DNS response DNS responses Just the first IP address found if it exists. The answer, then if answer dot data, then return, I guess it'll be answer dot data nil, something like that, I think. No. Invalid operator nil, mismatches type and string, type strings and untype nil. Oh, let's try again. It passed, but it also failed on the thing. Okay, let's see their solution, because I think mine is not so elegant. So DNS response. So yeah, they kind of do the same. One Marshall body DNS response. Marshall JSON error. So if the length of right, okay, that was the thing. So if length of DNS. Alright, okay, that's a simple way of doing it. If the length of DNS.answer is equal to 0, okay. Otherwise, you get the first one. Same way of going about it, I guess. So web addresses quiz. To recap, a domain name is a part of a URL. It's the part that tells the computer where the server is located on the internet by by being converted into a numerical IP address. We'll cover exactly how an IP address is used by your computer to find a path to the server in a later course. For now, it's just important to understand that IP address is what your computer is using at a lower level to communicate on a network. Deploying a real website to the real internet is actually quite simple. It involves only a couple of steps. Create a server that hosts your website files and connects it to the internet. Acquire a domain name. Connect the domain name to the IP address of your server. Your server is accessible via the internet. Okay, so it hosts your website files and connect to the internet. Okay. Which is a human readable label that converts to an IP address? A domain name. Why don't we require users to type in IP addresses directly into the to browse the web? We should also autoplay music on websites and use the blink tag. Domain names are easy for humans to remember. It's a better user experience. Okay, DNS. A domain name or host name is just one portion of a URL. We'll get to the other parts of a URL later. For example, the URL homestarrunner.com/tunes has a host name of homestarrunner.com. The https:// and /tune portions aren't part of the domain name to the IP address mapping that we've been talking about. The net/URL package. The net/URL package is part of Go standard library. You can instantiate a URL struct using the url.parse. And then you can extract just the host name. Okay, complete the get domain name from URL function. Given a full URL, it should return the domain or the host name. Simply return any potential errors. So past URL, an error, that pass, and then it's going to be raw URL. So then if error is not equal to nil, turn empty string and the error. Otherwise, return past URL dot host and nil. Happy days. So what is the domain name system? So we talked about domain names, but we haven't talked about the system that makes them work. DNS, or the domain name system, is the phone book of the internet. Humans type easy-to-read domains like Boot.dev. DNS resolves those domains to their associated IP addresses so that web clients can find the server they're looking for. Domain names are for humans, IP addresses are for computers. So it says, hey, what is the IP address for en.wikipedia.org? DNS says the IP address is this. How does DNS work? We'll go into more detail on DNS in a future course, but to give you a simplified idea, let's introduce ICANN. ICANN is a not-for-profit organization that manages DNS for the entire internet. Whenever your computer attempts to resolve a domain name, it contacts one of the ICANN's root name servers whose address is included in your computer's networking configuration. From there, that name server can gather the domain records for a specific domain name from their distributed DNS database. If you think of DNS as a phone book, ICANN is the publisher that keeps the phone book in print and available. DNS is a /an system that converts domain names to IP addresses. Programming language, IP address, domain name. What does ICANN do? Keep the DNS system up and running, control what you say online. Subdomains. So we learned about how a subdomain we learned about how a domain name resolves to an IP address, which is just a computer on the network, often the internet. A subdomain prefixes a domain name, allowing a domain route to route network traffic to many different servers and resources. For example, the Boot.dev website that you're on right now is hosted on a different machine than our blog. Our blog, found at blog.boot.dev, is hosted on our blog subdomain and the IP address / computer it points to. Assignment. I've updated the get-issues function from before. And now it accepts just a domain as input. It's convenient this way because it means if the API we're using ever changes its domain, we only need to update one variable. Problem is, there's a bug. The API isn't hosted on boot.dev, it's hosted on the API subdomain. Fix it. Okay, URIs. I think we do this. I think we get to headers and maybe the end of it. Let's see. Uniform resource identifiers. So we briefly touched on URLs earlier. Let's dive a little deeper into the subject. A URI, or Uniform Resource Identifier, is a unique character sequence that identifies a resource that is almost always accessed via the internet. Uniform Resource Identifier. Just like Golang has syntax rules, so do URIs. These rules help ensure uniformity so that any program can interpret the meaning of the URI in the same way. URIs come in two main types, URLs, URNs. We will focus specifically on URLs in this course, but it's important to know that URLs are one kind of URI. So Uniform Resource Identifier. Uniform Resource Identifier. URIs come in two main types, URLs, URNs. We'll focus on URLs of course, but it's important to know that URLs are just one kind of URI. So Uniform Resource Identifier. URLs are all URIs. Correct. All URIs are URLs. False. Sections of a URL. So URLs have quite a few sections. Some are required, some are not. Let's use the URL struct again. This time we'll pass a URL string and add all the different parts to a custom parsed URL struct. We'll learn more about each part later. Complete the new parsed URL function. It should return a parsed URL with all the parts of the URL. For example, given this URL, blah blah blah, new parsed URL should return a struct like with these fields. Use these fields and methods of the URL struct. Okay, so it's going to be parsed URL dot protocol scheme username parsed URL dot it's going to be username, isn't it? So user dot username, user dot password. This method returns two values, the password if set and whether it was set. Past URL.user. Okay. Past URL.user.password. Host name. So past URL.host name. Past URL.port. So past URL.path. Past URL.raw query. And then past URL.fragment. Scheme, whoops. So I guess it'd be password. So going to be password equals like that. Password is saying whether it was set. Can't do it like that. Oh, you have to do it like that. Okay. Peasy. So further dissecting a URL. So there are 8 main parts to your URL, though not all sections are always present. Each piece plays a role in helping clients locate the droids resources they're looking for. So you have the protocol, username, password, domain, port, path, query, and fragment. So protocol is required, username, nope, password, nope, domain, yes, port, no, defaults to 80 or 443. Path, no, defaults to /. Query, no, fragment, no. Don't memorize. Because names for the different sections are often used sloppily, and because not all parts of the URL are always present, it can be hard to keep things straight. Don't worry about memorizing this stuff. Like any good developer, now that you know about URL sections, you can always look up the specifics again in the future when you need them. The 8 pieces of the URL must always be present. False. Jello.app is a valid URL. Yep. Is a valid URL. Nope. The protocol. So, the protocol, also referred to as the scheme, is the first component of the URL. It defines the rules by which the data being communicated is displayed, encoded, or formatted. Some examples of different URL protocols: HTTP, FTP, mail to HTTPS. For example, HTTP :/example.com, mail to no reply at jello.app. Not all schemes require a /. The HTTP in a URL is always followed by : // All URLs have the colon, but the // part is only included for schemes that have an authority component. What's authority component? Authority. Many URI schemes include the hierarchical element for a naming authority, so that governance of the namespace defined by the remainder of the URI is delegated to that authority, which may, in turn, delegate it further. The generic syntax provides a common means for distinguishing an authority based on a registered name or server address, along with optional port and user information. The authority component is preceded by a // and is terminated by the next slash, question mark, or number sign at the end of the URI. Okay, as you can see above, the mail to scheme doesn't include the authority component, so it doesn't need to send slashes. Yeah, it doesn't have another slash at the end of it. In the Jello team menu, we show users the email addresses of their co-workers. We need that email to be clickable, to be a clickable hyperlink. When they click the hyperlink, their default email client should open with a new message ready to send to the address they clicked on. In the Jello team menu, we show users the email addresses of their co-workers. We need that email to be clickable hyperlink. When they click the hyperlink, their default email client should open with a new message ready to send the address they clicked on. Complete the get mail to link for email function. It should return a mail to URL with the given email thing. Okay, that's all that. So I guess return I guess we can just do like mail to plus email. URL ports. So the port in a URL is a virtual point where network connections are made. Ports are managed by a computer's operating system and are numbered from 0 to 65,535, though port 0 is reserved for the system API. Whenever you connect to another computer over a network, you're connecting to a specific port on that computer, which is listened to by a program on that computer. A port can only be used by one program at a time, which is why there are so many possible ports. The port component of a URL is often not visible when browsing normal sites on the internet, because 99% of the time you're using the default ports for the HTTP and HTTPS schemes, 80 and 443 respectively. Okay, whenever you aren't using the default port, you need to specify in the URL. For example, port 8080 is often used by web developers when they're running their server in test mode on their own machines. So let's have a watch of this.
If someone wants to communicate with a program on another computer, they make a request to its IP address, right? Easy peasy. But what happens if that computer is running multiple programs? And what if those programs are all trying to communicate at the exact same time? Well, that's what ports are for. Say I have a web server running on port 80, and I also have a database on the same machine running on port 5432. When my customers hit my server, I want them to talk to the web server and get a web page as the response. But I, as the website developer, still want to be able to remotely access my database directly so I can manually delete spam accounts and, honestly, more likely, I can even drop the settings table. But the point is still that the database is a separate process from the web server. And we don't want web traffic hitting it directly. Ports are what solves this problem. A port is just a number in the software layer, managed by the operating system, that allows us to route traffic to different applications on the same machine. There are 65,536 ports in most setups, which might feel oddly specific, but it's just because port numbers are represented as a 16-bit unsigned integer, so it's just 2 to the 16. For the most part, you can use whatever ports you want for your networked applications, but there are default ports for specific use cases. For example, HTTP traffic defaults to port 80. When you go to google.com, you don't have to type in google.com:80 because 80 is just the default port for the HTTP protocol. Or more likely, you're using HTTPS, which has a default port of 443. Now, if Google decided to run their production web servers on port 420 instead of 443, then you actually would have to explicitly type google.com:420 in the URL to get to the Google homepage, which would really suck. And that's why we have default ports for different use cases in the first place.
So if a port isn't present in the URL, the default is used based on the username protocol and domain name service domain protocol. So URL ports. So the port in the URL is, oh, we just read that. So only ports 80 and 443 can be used for HTTPS traffic. False. So URL path. So on static sites like blogs or documentation sites, a URL's path mirrors the server's file system hierarchy. For example, if the website https://exampleblog.com had a static web server running in its /home directory, then a request to the same domain exampleblog.com/site/index.html would probably return the file located at this. But technically this is just a convention. The server could be configured to return any file or data given that path. It's not always that simple. So paths in URLs are essentially just another type of parameter that can be passed to the server when making a request. For dynamic sites and web applications, the path is often used to denote a specific resource or endpoint. So assignment. The Jello server uses the URL paths to denote different resources, for example, /issues/projects. The entire server is hosted at the path /v1/courses REST API /learn-http. So all requests must be prefixed with that path. Update the URL in the code to fetch the project data by using the projects path. Projects. Query parameters. So query parameters in a URL are not always present. In the context of websites, query parameters are often used for marketing analytics or for changing a variable on the web page. With website URLs, the query parameters rarely change which page you're viewing, though they often will change the page's contents. That said, query parameters can be used for anything the server chooses them for, just like the URL paths. How Google uses query parameters. So open a new tab and go to google.com, search for the term hello world, take a look at your current URL. It should start with https://www.google.com/search ? Q equals hello plus world. Change the URL to say this hello universe and press enter. You should see the new search results for the query parameter hello universe. Google chose to choose query parameters to represent the value of your search query. It makes sense. Each search result page is essentially the same page as far as HTML structure and CSS styling concerned. It just shows you different results based on the search query. So query parameters are required in URL. Nope. In a website, query parameters rarely change. Which page is served, the contents of the page, marketing analytics information, which page is served. Cool. So on chapter 5, we could probably get this done. Maybe we do this another one, depending on how quick we get through this one. So what are HTTP headers? And HTTP header allows clients, and how long we got left on that? 16 minutes. So when this runs out, I'll stop. A HTTP header allows clients and servers to pass additional information with each request or response. Headers are just case-insensitive key value pairs that pass additional metadata about the request or response. HTTP requests from a browser automatically carry with them many headers, including but not limited to the type of client, the operating system, the preferred language. As developers, we can also define custom headers in each request. Headers in Go goes net/HTTP package. In Go, the net/HTTP package provides us with the necessary tools to work with HTTP headers. We can access headers through the header type, which is essentially a map of string slices. This allows us to perform various actions on our request and response headers, such as retrieving, setting, and removing them. Let me just have a look at, I don't remember like maps too well in Go, so let me just have a look at some maps in Go. Yeah, it's just an object, okay. So key string and then array of strings, or slice of strings. So creating a new request. So HTTP new request, get this. If there's an error creating a request. Setting a header on the new request. So request header.set that, and then making the request. So HTTP client.do request, defer, closing, and then reading the header from the response. So response header. Response.header.get, last modified, that delete, get header from the request. Okay, so assignment. So complete the get content type function. It takes a pointer of http.response as input and should return the content type header. Use the get method on the responsive struct header field to get what you need. Even though we've emphasized the need to close the response body, this is a mock response without body. Trying to .close will cause a panic. Okay, so I guess return. So response dot header dot get content dash type. Simples. Using the browser's developer tools. So modern web browsers offer developers a powerful set of developer tools. The developer tools are a front-end web developer's best friend. For example, using the dev tools, you can view the page's JavaScript console output, inspect the page's HTML, CSS, and JavaScript code, view network requests and responses along with their headers. The method for accessing DevTools varies from browser to browser. Common keyboard shortcuts, so Control-Shift-I. I think on here it's, yeah. In most browsers, you just right-click anywhere on the web page and click Inspect option. Follow this link for more information about how to access DevTools. So, the Network tab. While all of the tabs within DevTools are useful, we'll focus on the Network tab in this chapter so we can play with HTTP headers. The Network tab monitors your browser's network activity and records all requests and responses the browser is making, including how long each one of those requests and responses takes to fully process. So assignment, open the developer tools in your browser, navigate to the Network tab, refresh the page. You can now use the developer tools to view responses to requests your browser makes. True. Already knew that. After refreshing the page, what's the most common status code that you see in the Network tab? 200. So why are headers useful? Headers are useful for several reasons, from design to security, but most often headers are used for metadata about the request or response itself. For example, let's say we wanted to ask for a player's level from the Jello server. We need to send the player's ID to the server so it knows which player to send back the information for. That ID is my request. It's not information about my request. Authentication is a common use case for headers. If I ask Jello to complete a project, I need to provide authentication information that I'm logged in, but that auth info isn't the request itself, it's just additional information about the request. Assignment. Because we don't want any of our users accidentally overwrite another user's saved data, our backend team has required that we use the x-api-key header for all the requests to Jello servers. When we use different values, we're telling the server that we are a different person. There's a bug in our main function. It should get a project from the Jello API, log that project to the console, update the project and send those changes back to the server, get the project struct again and log the updated project to the console. Run the code in its current state to see the return values. Notice that the two structs that are logged to the console are the same. That's because the X API key they're using is different. The update isn't being applied to the same account that we're checking in the last get project response call. Use the same API key value in the last call to the get project response thing. So API key, new API key. Go. Network tab practice. So open your browser's DevTools, navigate to the network tab at the top. If you don't see the network tab, it should be in the drop down menu. Click it. Once you've opened the network tab, refresh this page. Poke around through the different requests that you see. Notice that you can select a request and see its request and response headers. Request headers are sent from your browser to the server. Response headers are the headers sent back from the server to your browser. You will use the information to find within the headers tab to answer the following questions. Header values are always numbers. False. The status code header in on the responses have string, object, or numeric values. Numeric. What is one of the values you see in the response headers for what is one of the values you see in response headers for the content type key? You might look at several requests. Let's have a look. Let's have a look at the page itself. For the content type key. Boot.dev, application/JSON, like that. Application.json. Boom. Right, we're nearing the end, so I think we'll just do a little bit of this and then we'll call it a night. Might actually be able to get this done into 2 scenes. Got 6 minutes left on the XP gain, so I think we'll just run it till then. Is anyone on Twitch? Nope, nobody on Twitch. So people on YouTube, hope you're having a good time out there. So HTTP methods get. Let's have a look. What are the lessons in here? So HTTP methods get. Why use HTTP methods? Blah 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 blah. Okay. So HTTP methods -get. HTTP defines a set of methods. We must choose one to use each time we make a HTTP request. The most common ones include get, post, put, delete. The get method is used to get a representation of a specified resource. It doesn't remove the data from the server, but rather gets a representation or copy of the resource in its current state. A get request is considered a safe method to call multiple times because it shouldn't alter the state of the server. Making a get request in Go. So there are two basic ways to make a get request in Go. The simple but less powerful way is http.get. The most but more powerful were http.client, http.newRequest, and http:/client.do. If all you need to do is make a simple get request to a URL, http.get will work. If you need to customize things like headers, cookies, or timeouts, you want to create a custom http.client and http.newRequest, then use the client's do method to execute it. Complete the get users function. It should call the http get using its URL parameter. Decode the JSON data from the response and return it. So we're going to have a response or error. And it's going to be http.get get URL. So then if error is not equal to nil, then just return nil error. Decode the JSON for response and return it. Now, let me try and remember this off by heart. So we're going to do, so decoder is equal to, let me try and remember. Is it like new decoder or decoder.new? Is it like .new decoder? Say var like response, or var I guess like var users is user, return users nil. So then decoder is going to be response, and then pointing at the users. Is it like this? And then I guess I think I got most of it there, but decoder, let me just have a look at the decoder thing again. Yeah, new decoder response. Oh, right, okay, whoops, got this part of that wrong. So then it's if error is decoder dot decode, and throw it to the users. Error is not equal to nil, then return nil nil error. Oh, JSON. Whoops, JSON.newDecoder. No pass response.body. Pretty sure that's that. Let's have a look at the solution, because what's the simpler way of writing that? Okay. Oh, right, okay, I guess it. That makes sense. I didn't do the defer thing. Why use HTTP methods? The primary purpose of HTTP methods is to indicate to the server what we want to do with the resource we're trying to interact with. At the end of the day, a HTTP method is just a string, like get, post, put, or delete. But by convention, backend developers write their server code so that the methods correspond with different CRUD actions. The CRUD actions are create, read, update, and delete. The bulk of the logic in most web applications is CRUD logic. Even a complex social media site is mostly just CRUD. Users create, read, update, and delete their accounts. They create, read, update, and delete their posts. It's CRUD all the way down. The four most common HTTP methods map nicely to the CRUD actions. Get is read, post is create, put is update, and delete is delete. These mappings follow convention, not law. Some APIs may use post for updating and creating. Some might just skip delete. HTTP methods map to CRUD actions by convention. To update a user account, I would probably use the put request. Post request. Right. Okay, it's 10 o'clock now, so I think we'll probably just stop there for now. We're on chapter 6, so we made some good headway. I'll probably be able to finish it next time. So, okay, that's it for tonight. We smashed through quite a bit, so it means we'll probably just beat this module in the next sitting, which kind of suits me actually, stuff, because then we can get into whatever's on next. I think it's like the Pokédex. I'm gonna have to reorganize the stream that was meant to be for tomorrow night, just because of things. So yeah. We'll definitely do on Thursday night, and then Friday, not sure, we'll see. But that's it for tonight. Thanks for watching. Hope you guys had fun and learned something, or it was just good. If you have a time, if you're watching coming back from the future, tell me where you got your time machine, and I'll see you all next time. So probably on